Hello and welcome. So these next few examples have to do with similar problems to the ones that you find on problem set 10. So we continue looking at applications of exponential functions, but now we're going to also work with the logarithmic function, which is crucial in helping us solve a lot of these problems. You can do some without the log, but most of them, the log is necessary in order to figure stuff out. So whenever the variable, the unknown, is in the exponent, you need to have a way of bringing it down from the exponent. You need to have a way of canceling out that base to get to the unknown. And the log, the function of the logarithmic function is exactly that. So the log is the inverse of the exponential. It gets rid of that base by doing log of both sides, and that helps you solve the problem. Okay, so here's an example. So you have 3 to the x plus 1 equals 12. You take the natural log of both sides. It really you can use any base as long as you do the same base to both sides, but the natural log is the one that's most commonly used. And then by the log properties, so there's a log property that says log of a to the b, the exponent comes in front. So this is b log a. Right? So this exponent of x plus 1 comes in front. You get x plus 1 log 3 equals log 12. Now this is just a number, so you divide both sides by log 3 in order to cancel this out. And then you have x plus 1 is log 12 over log 3, and then you subtract 1 from both sides. And then you plug that in the calculator and you figure out what the x is. So this is the standard procedure for solving an exponential equation. Okay? All right, you do want to, if you have the unknown in the exponent, you want to have the exponential part with the unknown to be by itself. So it has to be like the base to an exponent. It can't have anything else around it. Nothing multiplying it, nothing added, subtracted. You gotta isolate it and move everything else to the other side, and then you take the log of both sides. Alright, so let's look at application example. So we're going to kind of use that procedure to solve whatever equations we get from the application problem. Alright, let me fit this into here. Alright, so if $2,000 is invested in a continuously compounding savings account, and we want the value after 12 years to be $130,000, what is the required annual interest rate? If instead the same $2,000 is invested in a continuously compounding savings with R equals 6.4% annual interest, then when will the account value be $130,000? Okay, so we have a couple of problems in there that are related. So first of all, it's continuously compounded. That means the equation we start with is P equals A equals the amount, A equals the principal e to the RT. So principal is the initial money that you put in the account. R is the interest rate in decimal form. T is the time in years. E is that 2.71 number in your calculator. And A is the amount of money in the account at time T. Okay? So let's do the first part. So $2,000 is invested. So that's the original amount. And after 12 years, so T is 12, we want 130,000. So this is the amount that we want at the end. So 130,000 goes here. Let's fill in, we have E to the RT, so 12R. Okay, so R is our unknown, is in the exponent. So we're gonna need to use logs to get rid of the exponent. So before we use logs, we gotta get rid of any number next to the exponential. So we gotta divide by 2,000. Oops. Okay, so this cancels out. 130,000 divided by 2,000 is 65, is e to the 12r. We take natural log both sides, okay? Natural log has base e, which means that when you take the natural log of an exponential with base e, it cancels it completely, okay? So we have log of 65 equals 12r. R is going to be log of 65 divided by 12. Okay, now it's calculator time. So log of 65 divided by 12 gives me R equals 0.3479. Now changing this to percentage, this is a rate of 34.8% annual. Okay, no way that you're going to get this percentage rate from any account. Nowadays, interest rates nowadays are really low, and it's good because with the kind of pandemic and so on, it allows people to get loans to buy houses and things that they need and not pay much interest. But on the flip side is that if you invest money, if you try to put money in a savings account, the interest rate that you're getting is very low. Okay. So let's solve the second part of the problem. So we want to see how long it will take to get to 130,000 with that interest rate. So our problem is 130,000 equals 2,000 e to the r 0.064 times t. Right, so we know the r, but we're trying to find t. Same procedure. You're going to get rid of that 2,000 to start with. You get 65 equals e to the 0.64 t. We take log of both sides because that will cancel out the e. We have log of 65 equals 0.064 t. So t is log of 65 divided by 0.064. Okay, let's do that. Log 65 divided by 0.064. And we have t equals 65.2 years. Alright, so it takes 65 years at that interest rate to go from $2,000 to $130,000. Alright, let's look at another example. Okay, here we go. Alright, so in this example, we're gonna look at changing the base. So sometimes it's very useful to have the base, the base that's sort of natural to the problem that you're doing. So for example, you have the function a equals 202 to the t. Okay, this is exponential growth. So if you analyze this a little bit, the 200 is the starting value. So you have like 200 bacteria in a petri dish. All right, so this is the starting amount of bacteria. Now the base here, the 2, tells you that this value doubles every t, every time unit. So this is saying that it's doubling every t units. Okay, so it sort of, the exponential kind of makes sense to what's happening. Okay, but often people put these exponentials equation in terms of base e. That's the natural base for a lot of things that occur naturally. So E is sort of used by default. Partly, mostly, is because when you use the natural log in your calculator, it will cancel it out and make the calculations a little easier. But it doesn't make much difference really which base you use. But I think it's important to kind of know how to change bases. Okay, so let's say I want to change this. So instead of base 2, it has base E. It's still going to have the same starting value. So it's going to be 200. And this is like E to the KT. So what happens if you change it to base E is that it's going to insert like this growth rate, the constant here, next to the T. Okay, so to figure out what that is, we need to have, because in order for these to be the same, then E to the K has to equal to 2. So to solve for K, you take the log of both sides. We have this cancels out, so K equals log of 2. Okay, let's do that in the calculator. So log of 2 is 0.69315. 0.69315. Okay, so this is A to the T is 200, E to the 0.69315 T. Okay, so these exponential equations are identical. They're just using different bases. This is more intuitive. That it's going, the rate of growth is it's doubling. It's for every hour or every minute. This one is usually more used by default because it makes some calculations easier, especially when you get to calculus. All right. Okay, let's look at another one where we can use a change of base. Okay, let me copy it over here. Make it bigger so I can see it. All right, okay. So here's a function that exhibits exponential decay. You can see that it's a negative exponent. That means that it's decreasing. So I want to change this into like its natural base. So not with E, right? So basically what we do here, we're going to have A to the T is 4, and we're going to write this as E to the negative 0.2 to the T. Okay? And basically calculate E to the negative 0.2. So in our calculator, E to the negative 0.2. All right, so this is 0.8187 to the T. Okay, so now this is in the form of 4A times B to the T. That's standard exponential form. Okay, so what this tells me about my function is that sort of 4 is the starting value. So you're starting with 4. For of whatever you're interested in. Starting value when T is 0. Okay, and this right here is the base. This is what you're multiplying by each time. Okay, so according to this, the amount is decreasing because you're multiplying by a number that's less than 1, and you're basically you're going for each time unit, you're going to have about 81.87% of what you had previously. Okay, so 81.87% of the previous amount. Okay, so there's some sort of, decay rate. All right, cool. All right, let's see if we can find another problem. All right, here's another example that we can look at. of application that we can use logs and exponentials. There we go. Okay, lots of stuff with money. Yeah, but there's natural things like growth and decay of organisms, bacteria, radioactive decay with chemicals, but a lot of it that's very applicable is financial things. 10 years ago, you purchased a house valued at $80,000. Your plan is to sell the house at some point in the future when the value is at least $1 million. Assume that the future value of the house can be computed using quarterly compounding with an annual interest rate of 4.8%. How soon can you sell the house? All right, so we start with amount equals principal e to the RT. The amount that you want to sell it at in the future is $1 million. The present value of the house is $80,000. And the rate of growth is 4.8%. Oops. Sorry, wrong formula because we wanted, this is continuous compounding. It says it's quarterly compounding. All right, so let's start again. We have A is P, 1 plus R over N to the NT. So this is when it's compounded periodically. Okay, so quarterly compounding means that N is 4. All right, so my amount, $1 million, the original present value, 80,000, 1 plus 0.048 divided by 4 to the 4 times t. So we're trying to figure out how long it will take. All right, so let's do divide by 80,000. All right, this is going to go away. 1, 2, 3, 4, 5, 6 divided by 8, 2, 3. And this is 12.5 equals, I'm going to do the calculation parenthesis here. 1 plus 0.048 divided by 4. This is 1.192 to the 4t. All right, we have our t is in the exponent, so we're going to take the log of both sides. Right, so because this is not a base of e, the exponent comes down. So we have log of 12.5 equals 4t, log of 1.192. Isolate the t, so we got to divide by log of 1.192. And also divide by 4. All right, everything here cancels. We get t equals calculator time, log of 12.5 divided by log of 1.192 divided by 4. T equals 3.6 years. All right, let me check on that. That does not sound right. I think I made a mistake here. Okay, 1 plus 0.048 divided by 4. Oh yeah, I wrote 9. Yeah, I don't know what happened there. This like takes... It's no way that it takes 4 years. All right. Yeah, this was 1.012. Makes a lot of difference. Log. All right, take the 4t down. Log of 12.5, 4t, log of 1.012. Divide by 4, log of 1.012. All right, log of 12.5 divided by log of 1.012 divided by 4. That's more reasonable. T equals 52.9 years. All right, that makes a lot more sense. You can't have a house go from 80,000 to 1,000,000 in 3 years. That's why math, mistakes are made. You write, don't type the right numbers in the calculator. That happens all the time. The important thing is, like, when you get your answer, does it make sense? And if it doesn't, check. All right. So that's my lesson learned there. Don't be afraid of mistakes in math. They happen all the time. It's just like kind of catching them. All right. Let's see if I have another example. Let's look at this one with getting away from money a little bit. Okay, so we're going to look at an example that has to do with sound intensity for a loudspeaker. All right, so that's the beginning of the problem. And here's another bit here that continues the problem. All right. A loudspeaker manufacturer advertises that their model number 801 speaker produces a sound pressure level of 87 decibels. So that's the unit measured for sound when a reference tone is applied. A competing speaker company advertising that their model X1 speaker produces a sound level of 93 decibels when fed the same test signal. What is the ratio of the two sound intensity produced by the speakers if you wanted to find a speaker which produces a sound intensity twice of that of number 801 when fed a test signal? What is its sound pressure level? All right, so we need a basic equation. So the equation for sound intensity is the sound pressure level, beta, is equal to 10 log base 10 of I divided by I0. Okay, so let's unpack this a little bit. So this is the decibels. This is the sound pressure level. Okay, so when you're given decibels, that's where the number goes. 10 log base 10. Okay, so these are measured in a log scale. So I is the intensity, and I0 is that sort of initial intensity. That's like the test tone kind of deal. So initial intensity. Okay, so let's figure out some stuff. Okay, so let's say we have these two speakers. So we have the number 801 speaker, and we're told that 87 decibels is going to be 10 log base 10. I'm going to call this I1 over I0. So kind of the intensity of that first speaker compared to the initial intensity. And then we have the X1 speaker. Decibel level is 93. 10 log base 10. With intensity I2 when compared with that same test signal. So the I0 is the same for both. All right, so let's solve each of those for the intensity. So I want to solve this I1 and I want to solve this for I2. All right, because I want to compare I want to find the ratio between the two sound intensities. Okay, so the intensities are going to be found in terms of I0, in terms of the initial intensity, and that's fine, because when you do the ratios, because you're comparing with the same test signal, these are going to cancel out. Okay, so we got to solve for I1. So in this first equation, we're going to do 87 divided by 10. We got 8.7 equals log base 10 I1 over I0. We're going to change this to an exponential. So this is we're starting with the log equation. We're trying to get rid of logs. So we're going to do 10 to the 8.7 and 10 to the this to cancel out the log. So we have 10 to the 8.7 equals I1 over I0. So I1 is equal 10 to the power 8.7 divided by times I0. Okay, so don't bother doing 10 to the 8.7 is a big number. We're just going to leave it like this. All right, now let's solve this one. So divide this by 10. We have 9.3 is log base 10 I2 over I0. Do 10 on both sides to cancel out the log. 10 to the power 9.3 equals I2 I0. So I2 equals 10 to the 9.3 divided by I0. So that's the intensity of the second speaker as compared to that test signal. All right, now we want to find the ratio between these. So let's do I2 over I1 because I2 is bigger. So 10 to the 9.3 I0 divided by 10 to the 8.7 I0. These cancel out. And then the exponents subtract. So 9.3 minus 8.7 gives me 0.6. All right, let's do 10 to the 0.6 in the calculator. We get about 3.98, which is approximately 4. Okay, so that means the speaker X1 is 4 times as loud as speaker number 801. Okay, so in terms of decimal levels, there's only from 87 to 94 decibels. That's like 6 decibels difference. But in terms of the sound pressure that's put on your eardrums, the X1 is 4 times as loud as the other speaker. That's pretty cool. All right, so what other question is here? If you want to find a speaker which produces its sound intensity that's twice that of the number 801, what is the sound pressure level? All right, so we are working with a problem. Let's have a I3 speaker, and we want that when compared to the 801, we want that to be 2. Okay, so we want I3 to be twice I1. Okay, so we know I1, the equation for it is this. Okay, so we have 2 times 10 to the 8.7 I0. I3, so let's see, we basically are looking for this unknown intensity pressure level. This is 10 log base 10 I3 over I1. If we solve this, we have B over 10 equals log base 10 of I3 over, I0. 10 on both sides. We have I3 is going to be 10 to the beta over 10 times I0. Okay, so that's what we're comparing. This is 10 beta over 10 I0. All right, so we're solving for beta. So cancel this out. We have 10 beta over 10 equals 2 times 10 to the 8.7. All right, we're going to do log of base 10 on both sides. All right, to cancel this out, so beta over 10 equals log base 10 of 2 times 10, 8.7. So beta is going to be 10 times log base 10 of 2 times 10, 8.7. All right, so I'm going to plug this in the calculator. 10 times log base 10 on your calculator is the LOG button. So 2 times 10 to the power 8.7. And I get beta is 90. Okay, so 90 decibels is going to be twice as loud as a speaker with 87 decibels. All right, that's it for the examples that have to do with problem set 10, having some logarithmic and exponential equations, and hopefully this will help you with the problems in that problem set. All right, see you guys later.